LEDs and photodiodes unlock biotech. LEDs and photodiodes are two of the most common integrated components in the world, found in phones, wearables, remotes, and more. But we've barely begun to use them as biomedical sensors for identifying molecules. This video explores how these tiny light-based tools could help unlock the next generation of biomedical diagnostics and molecular detection. Detecting molecules with light. If we want to use LEDs and photodiodes to detect molecules, we need to understand how they work as a sensing pair. LEDs shine light into a material like tissue, breath, or fluid. As the light passes through, some is absorbed or altered by the molecules inside. Photodiodes detect the light that comes back, capturing changes in intensity and wavelength. Today, this method is used to detect just a few molecular signatures, but with the right information systems approach, it has the potential to transform the entire field of molecular diagnostics. A real-world molecular sensor. This kind of molecular sensor that uses light is already being used, but only in a few places. One example is a wearable glucose monitor that shines near-infrared light into the skin and reads the light that comes back. It's about the size of a smartwatch and straps to the wrist. Inside, it uses a handful of tiny LEDs and photodiodes, usually just a few of each, to scan tissue and capture subtle changes in light absorption. The signals are processed by a small chip in the device, or sometimes sent to an app or cloud service for deeper analysis. It doesn't detect glucose molecules directly. Instead, it reads how light is absorbed by the surrounding tissue and infers glucose levels from that. It's not always precise, and the devices can cost hundreds of dollars, but it proves that this light-based biomedical sensor works. The limits of glucose detection. Light-based glucose sensors prove that this technology can work, but they also reveal its limitations. When the device shines near-infrared light into the skin, that light interacts with everything it touches. Water, fat, proteins, and glucose all absorb and scatter it in slightly different ways. But glucose has a weak signal, and it's surrounded by a noisy soup of other molecules. The sensor can only use short, low-power light pulses, because too much energy would heat the tissue and become invasive. Most of the light is absorbed or scattered, and the photodiode captures only the part that reflects back. Factors like skin thickness, hydration, and temperature can shift the signal, so these devices require constant calibration. Even with modern algorithms, the results can drift, often missing by 10 to 20%. They typically sample just once or twice an hour to save power and reduce noise. But that also means short-term glucose spikes can be missed. It works, but the precision and reliability still fall short of what we need for broader use. Why won't this tech scale? We've just seen how light-based glucose sensors work, but why aren't we using the same approach to detect thousands of other molecules? Each new molecule requires its own setup, different wavelengths, different calibrations, and custom signal processing. Even when a molecule has a unique optical signature, that signal is often faint and buried under noise from other molecules. Finding and isolating that pattern takes trial and error, a process that's expensive, time-consuming, and highly specific. That's why sensors today are still one-target tools. A general-purpose molecular detector remains out of reach, at least using this approach. A universal biomedical sensor. We're still in the early stages of light-based molecular sensing, building devices that target just one molecule at a time, using custom setups that are expensive to develop and easily disrupted by noise. These systems work, but they're fragile, sensitive to real-world conditions, and narrow in scope, designed to detect a single biochemical signal rather than the broader complexity of human biology. This approach doesn't scale, and that's the real obstacle. But what if we stopped designing for one molecule at a time and started building flexible arrays that collect massive data sets? Data that looks like noise at first, but contains much more. With the right processing, We could extract molecular patterns just like we decode speech or recognize faces, not by building better sensors, but by building better information systems. That shift opens the door. The core components already exist and are scalable. What we've been missing is the right blueprint, an information systems approach that connects the hardware to real molecular insight. That blueprint exists, and in the next slide, we'll show you where to find it. The blueprint starts here. If we want to build a universal molecular sensor, we need more than just parts. We need the right framework. Darwin's Machines 2024 offers that framework, a new way of thinking about sensors, computation, and information itself. It explains how biological systems organize data, how information flows through networks, and how those same principles can be applied to hardware, creating tools that scale, adapt, and decode the physical world. Machines that can detect 1,000 different molecules per test, at pennies per test, could be built today using this approach. I'm looking for people who want to help me build this now. If that's you, let's talk.